So this is enough to talk about the sampling distribution for X bar, which is the first step that we need to do in any kind of inference, is what does that X bar act like? Well, in the case of the single proportion, that P hat had a normal distribution. It was centered at the population parameter, and it had a standard deviation, which was the SD we had up here. Well, that's exactly what we'll have in this case. X bar is distributed as the normal, the mu, and that standard deviation. Okay? Under these conditions, if I know this sigma, so I know this value from the population, I can calculate z's. That's going to be x bar minus mu divided by sigma over root n. So that's the same as what we had before, essentially. I've replaced this with a little bit different form than what we had for the proportion, but it's simpler in this case. And we have this x bar. Now what this is going to do is give us our z distribution centered at 0, going in plus and minus 3. Okay? So this should all be very straightforward, right? Just a minor twist on what we had in the previous section. Right? Yes. Okay. So this shouldn't be too bad to work with, except for one thing. What did we say about population parameters? The whole point behind this inference is we don't know the value of mu, correct? And that's because we can't get at this population. I don't know the value of mu. Where am I going to get the value of sigma from? That's what we're going to have to do, yes, isn't it? Just like we did for mu, isn't it? So we can't use this. This doesn't work. Okay. We will have situations where we'll apply things like this, but they're all rather arbitrary kinds of situations. We'll have an example we'll look at here in a minute that will do it. But there are situations where they tell us what the value of mu and sigma are, but in reality, we generally don't know that. So in inference, we're not going to know what this value of sigma is. So what should I use in place of sigma? Sure. That means that I'm going to do a transformation now. Instead of a z, it's going to be a t equal to x bar minus mu over s over the square root of n. Now I've got something I can work with, right? This is from the sample. This is from the sample. This is normally the thing that we're hypothesizing about, so we'll get that from the hypothesis later on. So this is all something we can work with. How do you think this is distributed?
I got a question. What's T?
These are both standardized statistics. T will be the equivalent of the z that we used in the previous ones. So these are z tests. These here will be t tests. So, what do you think the distribution of this looks like?
Bell shape.
Good. That's exactly what it looks like. But there's a hitch to it. It couldn't be quite that simple. It is a bell shape. It is very similar to the normal distribution that we have here. However, the problem is that these look very much the same, don't they? The difference is that in place of this sigma, I have an s. S is an estimate from the sample, just like X bar is an estimate from the sample. So when I estimate S, I don't exactly get sigma, do I? I get something that is similar to sigma, maybe close to it, but it is going to have some variability to it. So what's happened is that by putting S in here, I've added uncertainty into this value that wasn't in the Z. If I increase the uncertainty of this bell curve, what should happen to it? Should it get taller or flatter? Should get flatter. That's what a t-distribution looks like. It'll be centered at the same spot. It's still a bell shape, although it's a much flattened bell. Don't worry too much about the asymmetry I drew in there. That's me, not the curve. So it's a flattened version of this normal distribution. Okay? Other than that, it's going to be very similar. But that also means that we can't use table 8.1 to look up values. We're going to have a different table to look up values in. Okay? Characteristics of this t-distribution: it'll be centered at 0, same as the Z was. How flat this is going to depend on the size of our sample. Why should that be?
Bigger samples more accurate?
Sure, exactly. What caused this to flatten out was this S wasn't very close to sigma. It wasn't exactly sigma. The bigger the sample is, the more accurate that S is at estimating sigma. So the bigger the sample is, the closer this is to that. Okay? So for very small samples, it's extremely flat like this, very wide. For larger samples, it gets narrower, and as the sample size gets larger and larger, it gets closer and closer to the normal distribution. When the sample size reaches infinity, actually much below infinity, when the sample size gets quite large, usually it's somewhere on the order of a few hundred to 1,000, the distribution becomes essentially the same as the normal distribution. But for anything below that, you have this flattening that occurs, and so you have to look it up in a different table. Okay? So that's the next wrinkle that we've got in this. Yes?
So is that accurate for anything under like 20?
Well, this is reasonably accurate for things well under 20. The problem is that what you get is you get a very broad or very wide distribution, and so it's very hard to show anything as significant. You also get very wide confidence intervals because the variation is so high. And that's because when you're estimating that sigma with this S, it's a pretty bad estimate when you get small samples.
So, I mean, are your standard deviations just bigger there? Because
Yep, exactly. What's happening is that the overall standard deviation is increasing for this particular distribution. It's getting wider.
How do you get S?
S is just the standard deviation calculated on the sample. So use the standard calculation for standard deviation. Apply that to the data in the sample. That's your S. In most cases, we'll simply give it to you. We will read it out of SPSS. Some other professors don't like this, but I actually don't make it calculated any place because I've never seen any particular value to actually calculating the value of S. What I want you to do is know what it is. Okay?